So we are now going to look at 11.3, which is on solubility. Sorry, I'll just scroll down. Okay. And so this is covering solutions and mixtures. It's covering solubility and like molarity and things like that. So first of all, something that you probably already know, but molarity is moles per liter. And so reminder, for example, 3 molar HCl means 3 moles of HCl per liter of solution. So an application of molarity, or a type of calculation you need to know for this class, is the dilutions formula. Molarity 1 times volume 1 equals molarity 2 times volume 2. For the volume units, it's okay if you put them in milliliters. It's okay if you put them in liters, but keep in mind it needs to be consistent. So if the left-hand side, technically it's supposed to be liters, but if the left-hand side is milliliters and you use milliliters on the right-hand side, you're going to be okay, as long as you don't go back, you mix up the two sides. So, how many milliliters of 8 molar HCl to make 250 milliliters of 1 molar HCl? So this is how we're going to use this formula. So M1 is 8 molar, and then the volume that we need of it is unknown. Okay? So this is asking how many milliliters of 8 molar would we add to water to make 1 molar. So our final volume is 250, and then our final molarity is 1. Okay? So then we can solve for this. So we do 1 times 250 divided by 8. And if we do that, we get 31.25 milliliters. What does that mean? Milliliters of the 8 molar HCl. So what does this mean? This means that we're saying that you would take 31.25 milliliters of 8 molar HCl and add it to water. In this case, there's 250 milliliters of water, so you'd be adding about 218.75 milliliters of water. I say about because we'll hopefully do at least one lab where you use a volumetric flask. And when you use a volumetric flask, for example, you would fill up until you hit the line to get the volume exact, instead of adding a specific amount of water. But if you could just, if it doesn't really matter, you can just add the water to get it up to the amount that you need. If there are 10 milliliters of 3 molar, actually, and this isn't really the best case of using a volumetric flask. The best case to use it would be if you had like a chemical that wasn't a liquid, wasn't aqueous already, and you made it aqueous, added it to the flask, and then you add water to get up to that line. So you could just use a graduated cylinder here for this one. But anyways, if there are 10 milliliters of 3 molar HCl, add how much water to make 1 molar HCl? Well, we're going to use the formula again. So we have 3 molar times 10 milliliters of it. So what would be the final solution? What would be the final volume if it was all 1 molar? Well, if we do the math here, we'd get volume 2 equals 30 milliliters. But that is not our final answer, because that's the final volume. We're starting with 10. So if in here, in the above question, what will the total volume be? The total volume will be 30 milliliters, but we're adding 20, because what V2 means is V2 means that the final volume is 30. It doesn't mean you add 30, okay? So it's saying if you start with 3 molar 10 milliliters, your final will be 30 milliliters of 1 molar. And so what that means is that the final volume is 30 milliliters, but the difference in volume added is 20. So hopefully that makes sense. Using that formula, we'll have some practice problems and let me know if you are confused. Solutions and phases. As you can see through the examples given so far, solutions can be solids, liquids, or gases. Regardless of phase, in a homogeneous mixture, the properties of the mixture do not vary throughout. So if it's homogeneous, it doesn't matter what type of phases are in it, they don't vary. In a heterogeneous mixture, the properties will change as the percent composition in various areas changes. Solubility is the maximum concentration that may be achieved under given conditions when the dissolution process is at equilibrium. The reason it says given conditions is solubility can change with especially temperature and also pressure, especially if we're talking about like a gas. And what the standard tells us is essentially that like dissolves like. So something with a similar polarity, for example, will dissolve better. So something that can hydrogen bond with water will generally dissolve a lot better with water than something that just has London dispersion forces. So like dissolves like is the general rule. So in water, stronger attractions between the solute and the water will increase the solubility of the solute. So generally, things that dissolve better in water and have a higher solubility are polar and/or can hydrogen bond with water or are ionic. So salts dissolve well in water because of the cations and anions that have charges that can interact with the partial charges of water. Something is saturated when a solute's concentration is equal to its solubility. In other words, it can't get any more concentrated than that. If you added any more, it would just go to the bottom of the container and sit there. And unsaturated just means you could add more because the maximum solubility has not been reached. Supersaturated is when something exceeds its normal solubility. So allowed to go to equilibrium, it would change. So for example, if we have a soda can, we can add a lot of pressure to basically push more gas into the liquid. But if you leave the can open, right, air is going to escape over time. And if you leave the can open for a long time, it will go flat as it reaches equilibrium, and there will be less gas in the water. As for any solution, the solubility of a gas in a liquid is affected by the intermolecular attractive forces between solute and solvent species. So some gases, even if they're a gas, if they interact better with water, it can increase their solubility. Unlike solid and liquid solutes, however, there's no solute-solute intermolecular attraction to overcome when a gaseous solute dissolves in a liquid solvent. So for example, what that's saying is we talk about how when there's solid, for example, added to water, let's take NaCl. Na and Cl, it takes energy to pull them apart. It takes energy to pull the water molecules apart, and then energy is released when the Na and or Cl come with the water again. Right? So there's those three steps to take the ions apart. That's step one. Then two, you have the waters that are already interacting with each other. And so now you are pulling those apart. But then step three, that releases energy. So these are increases of energy. Step three, that releases energy, is when now the ions are interacting with the water. However, for gas, we don't have this first step because the molecules are not next to each other. So because they're not next to each other, there's no energy to pull them apart because they're already separated since they're in gaseous phase. You can see here what is the relationship between the pressure of a gas in a liquid and its solubility. Why are carbonated beverages a wonderful example of this? Well, here it shows us the solubilities of these gases in water decrease as the temperature increases. So you can note it's actually the opposite of like adding salt or something where the solubility is going to increase with temperature. And so carbonated beverages are also an example. We keep them cold. The solubility is higher, actually, when they are really cold. And I think I wanted to say more about this, but I don't think it's necessary. So, because it's not really covered too much in AP Chem, even though it's in the book. Additionally, gas solubility increases as the pressure increases. So this is a nice figure. Opening the bottle of carbonated beverage reduces the pressure of the gaseous carbon dioxide above the beverage. The solubility of CO2 is thus lowered, and some dissolved carbon dioxide may be seen leaving the solution as small gas bubbles. So you open it, and CO2 is leaving because the pressure that was keeping it in now is not there, so it can escape. Miscible or miscible means that two liquids can be mixed in any proportion. So this would be something like ethanol and water, where you can have 50-50%, 50% of each, or you can have 10-90. You could have 10% ethanol, 90% water, or 90% ethanol, 10% water. So any mixtures, and they will mix just fine. And again, remember, like dissolves like. So like ethanol is an alcohol, so it can hydrogen bond with water. So like dissolves like. They're really similar, like dissolves like, so that's why they're miscible. And so miscible liquids are typically those with very similar polarities, like ethanol and water. Immiscible are two liquids that do not really mix, like a nonpolar oil, right, and water. And partially miscible are in between, moderate mutual solubility, like bromine in water, for example. And here's an example. You can see that like in the description here, the top layer in the mixture on the right is a saturated solution of bromine and water. So some of the bromine mixes with the water, but a lot of it doesn't. So it's partially miscible. 11.4 we're going to skip. It's not covered on AP Chem. And so we'll stop this video here. And the next one we'll talk about 11.5.